Okay, this is the lesson on 3.6, local linear approximations and differentials. This is a section that we have to spend our time being a little bit more detailed about. There are things that we're going to talk about that I definitely want you to be journaling. There are things that I'm going to want you to know, obviously from the lesson that makes sense, but there are very specific details I'm going to want you to know from this lesson. Now, interestingly enough, here at the beginning of the lesson, between the two red lines here, it says, up to now we've been interpreting dy dx as a single entity representing the derivative of y with respect to x. That's not true. It's probably true of the textbook, but ever since I introduced dy dx to you in class, I haven't wanted you to think of it as a single entity. I've wanted you to view it as the ratio of two differentials, or the ratio of two infinitesimals. That's what I wanted you to view it as, not as a single entity. So this part here is not true, only because of I wanted to introduce this concept that it's a ratio far sooner than what they typically do. Let's talk about increments. If the value of a variable changes from one number to another, then the final value minus the initial value is what we call an increment. And so delta x is called an increment, and it's equal to x1 minus x naught. So we can think of delta y as the difference of two y values, y1 minus y naught, which can be rewritten as f of x1 minus f of x naught. So delta x, or delta y, the change in x produces a corresponding increment change in y. Okay, let's go and zoom in on this picture. Make sure we understand the picture. So here's x naught, here's f of x naught, here's x1, here's f of x1. The change between x1 and x naught is what we call delta x, or it's the base of a right triangle. The change in y, what we call y1 minus y naught, is delta y, and that's the height of the right triangle. And so if you take the ratio of delta y to delta x, what you end up getting is the slope of a secant line. That's what you get when you take the ratio of the two changes, or the two deltas. That's going to be important to remember. Now, increments can be positive, negative, or zero, depending on the relative positions of the initial and final points. An increment in x is positive if the final point is to the right of the initial point, negative if the final point is to the left, and zero if the initial point and final points coincide. So if we observe the expressions delta x is equal to x1 minus x naught, and what delta y is equal to y0, y1 minus y naught, notice we can change this to represent an update. So in other words, x1 is an update of x naught. You take x naught and you simply add the change, and you've updated, and you've gotten x1. Same thing with y. y1, you take the y naught, update it with delta y, and you get y1. This simply states that the final value of a variable is equal to its initial value plus its increment. That's probably worth journaling right there, these equations in that sentence. Delta y can also be viewed as the difference of f of x naught plus delta x minus f of x naught. It's a good idea to journal that equation because we're going to use it. Sometimes it is convenient to dispense with subscripts on the initial and final values of a variable, in which case the initial and final values of x would be denoted as x and x plus delta x. And the initial and final values of the variable y would be denoted as y and y plus delta y. With this notation, the symbols of x and y play dual roles. They play two different roles. They serve as the names as well as the initial values of the variables. However, this rarely causes any confusion. With the subscripts omitted, formula 2 simply becomes this. Delta y is equal to f of x plus delta x minus f of x. And this, I don't want to harp on this too much, but I will. The ratio of delta x to delta y to delta x can be interpreted as the slope of the secant line. Recalling the definition of a derivative, dy dx, that's the ratio of the infinitesimals, or the differentials, is the limit as the change in x goes to 0 of delta y over delta x. That's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And so now let's go ahead and zoom in on this picture, make sure that we understand it. So here's the point x, and here's f of x. Here's x plus delta x, and here's f of x plus delta x. So the change in x, the change in y, so the ratio delta y to delta x is the slope of this secant line. But as this shrinks to 0, notice the arrow, this point, x plus delta x, slides into x, and this point here, which is f of x plus delta x, slides into f of x. And so what was the slope of a secant line becomes the slope of a tangent line once we take the limit. And so that's how the notation is being used. Differentials. Two mathematicians, Newton and Leibniz. They actually, historically speaking, invented calculus at the same time. So there's a little bit of debate about who is the original author of calculus and who's the secondary. So we attribute calculus to both of them. So when Newton and Leibniz independently published their discoveries of calculus, they each used different notations for the derivative, and battles raged for more than 50 years over which notation was better. The English obviously preferred Newton, since he was English, and the French obviously preferred Leibniz, since he was French. In the end, Leibniz notation, dy dx, won out because it produced correct formulas in natural ways. For example, the chain rule. Here's Leibniz notation. dy dx is equal to dy du times du dx. The symbols dy and dx that appear in the derivative are called differentials. And our next objective is to define these symbols so that dy dx can actually be treated as a ratio. But that's not a worry for us because we've been treating these as a ratio since the very beginning. For this purpose, regard x as fixed and define dx to be an independent variable that can be assigned an arbitrary value. So therefore, the equation dy dx equals f prime of x can now be written as dy, differential y, is equal to f prime times differential x, provided that differential x is not 0. If we just divide both sides by dx, then we get the natural dy dx is f prime of x. Thus, we have achieved our goal of defining dy and dx so that their ratio is f prime, because differential y with differential x is nothing more than the slope of the tangent line, where the slope of the tangent line is the slope of the tangent line. Sorry, I didn't mean to be repetitive there. And it can be viewed as the corresponding rise and run of the tangent line. It is important to understand the distinction between the increment, delta y, and the differential, dy. Those are two completely different creatures. So let's go ahead and look at the picture and see if we can understand the difference between them. When you talk about dy, what you mean is the rise of the tangent line. So dx is the run of the tangent line. dy is the rise. Now, it is possible to let delta x equal dx. We can let these arbitrarily become the same value. But when it comes to dy and delta y, you're talking about two different creatures. Delta y is the rise of the secant line. So if I put a point here and connected this point to that point, it would be a secant line. And that is primarily the difference between the two. Delta y is the rise in the secant, whereas dy is the rise in the tangent. And those are the two things I want you to make sure that you journal this picture and put into a short sentence or paragraph what we just spoke about here in this lesson. So maybe pausing the video now is a worthwhile endeavor, and getting this picture in your journal and then writing a paragraph or so about what we just talked about. Delta y is the rise in the secant, dy is the rise in the tangent. However, we can on occasion let delta x and dx arbitrarily equal each other. Okay. It is important to understand this distinction. I'm probably going to repeat myself, but I just want to make sure that I get this point across between the increment delta y and the differential dy. To see the difference, let us assign the independent variables dx and delta x the same value so that they are the same. Then delta y represents the change in y that occurs when we start at x and travel along the curve, which would produce the slope of the secant line, until we have moved delta x, or dx units, in the x direction, while dy represents the change in y that occurs if we start at x and travel along the tangent line. And that's really the key here, along the tangent line. Example 1, if y is equal to x squared, then the relation dy dx equals 2x can be written in differential form. So you got to know what differential form is, okay? So here's differential form, dy equals 2x dx. Then, when x equals 3, knowing x equals 3, this means that dy is equal to 6 dx. Now, that's important, and let me try and explain why that's important. I'm going to go back to this picture. What this means is, when you have something in differential form, you're following the tangent line. So that means that if I change, let's pretend dx is 2. And what I do is I change 2 units away on the x-axis. Well, what's 6 times 2? It's 12. And what that means is that the tangent line will rise up 12 units when I change 2 units. So a differential form helps me understand how the tangent line is changing. By knowing dx, for every amount dx, dy will always change 6 times that amount. And so that I can always keep record of how the tangent line is changing. That's what differential form is all about. Example 2, let y equal the square root of x. Let's find differential y and change in y at x equals 4 by using differential x and delta x to be the same amount. Then let's make a sketch of y equals square root, showing differential y and delta y in the picture. Now remember, in order to find differential y and delta y, we're going to have to use the formulas that they gave us. Let's see if I can scroll to those formulas relatively quickly. So here's the formula for delta y. We could also use this corresponding formula here. And the formula for differential x, or differential y, is right here. So make sure you get those 2 formulas written in your journal and you make a distinction between them. So, okay. First, let's find differential y, which is the square root of x plus delta x minus the square root of x. Well, we know the change in x is 3 and x is 4, so this can be easily calculated. That's the square root of 7 minus the square root of 4, which is 0.65. Now, dy dx can be written as this, so therefore differential y is 1 over 2 square roots of x dx. Plug in the values that we know, and we get 0.75. Now, looking at the difference between the two. Here's 4. Let me zoom in on this. Here's 4, and I go a difference of 7. Now, along the curve, the delta y, I've changed a value of 0.65. But along the tangent line, I've changed a value of 0.75. So the value that I've changed of 0.65 was starting to put my cursor here, change dx or delta x is 3. Going up is a change of 0.65 right here. Going back, changing 3, and delta y is a change of 0.75. Not too bad, huh? Not too different, but they are different. And that's what I want you to see. I want you to see how they're different. Okay, this is going to lead us into a concept called local linear approximation. Points of differentiability for a function f can be described informally in terms of the behavior of the graph of f under magnification. If p is a point of differentiability for a function f, then stronger and stronger magnifications at point p eventually make the curved segment containing p look more and more like a non-vertical line, the line being the tangent line at p. And for this reason, a function that is differentiable at point p is said to be locally linear. So, for example, here is a point p that is a point where it's differentiable. And as we continue to zoom in and magnify this region right here, it looks less and less like a curve and more like a straight line. And this is what we mean by locally linear. Locally linear. But over here, in this example, here's a point P that is not differentiable. And so no matter how much you zoom in on that point, it never looks like a line. You can always see that it's not differentiable. And so this picture would be a prime example where local linearization cannot be used because the point P is non-differentiable. All right, so to capture this intuitive idea analytically, observe that the tangent line through the point x naught, f of x naught, has a slope of f prime of x naught. So the point slope form of the equation is y minus f of x naught equals f prime of x naught times x minus x naught, which we can rewrite as simply adding this term to the other side. Y equals f of x naught plus f prime of x naught times x minus x naught. This equation, to say that this line closely approximates the curve for values of x near x naught, we mean that the approximation f of x is approximately f of x0 plus f prime of x naught times x minus x naught. So this equation is called the local linear approximation. And if you want to treat x minus x naught as a change in x, you can replace this further by simply saying, let's see, let me just go ahead and read this. Gets better and better as x goes to x naught. We call number 6 the local linear approximation. An alternate version of this formula can be obtained by letting delta x become x minus x naught, in which case we can express this as f of x plus x delta x is approximately f of x naught plus f prime of x naught times delta x. So let's look at an example. Find the local linear approximation of f of x equals sine of x at x naught equals 0. Now what I've done is I've made a picture of the sine right here. And let's go ahead and grab this and center this as best we can here. Okay. So what I want to do now is I want to zoom in around, I hate that bell. Okay, I want to zoom in around x equals 0. And look what happens when I start to zoom in around x equals 0. Do you still see the curve? How about now? How about now? Ah, look what just happened. It looks more and more linear. So as I go out, here's 0.25. So it really looks like a line, mostly right here. If I go to negative 0.25, it still looks like a line. So the point is simply this. If I used the equation of the tangent line in this region, my approximation would probably be really good. So that's the whole point of local linear approximations. It's using the tangent line to approximate the function wherever the tangent line looks like the function when it's zoomed in as looking like a line. That's probably more complicated than it needs to be. So let me go ahead now and let's do this together. So part A, find the local linear approximation of f of x equals sine of x at x naught equals 0. Then we want to use the local linear approximation obtained in that piece that we did to approximate the sine of 2 degrees. And compare your approximation to the result produced directly by your calculating device. So, okay, since f prime of x is the cosine, it follows from formula 6 that the local linear approximation will be sine of x is approximately the sine of x naught plus cosine of x naught times x minus x naught. Thus, the local linear approximation at x equals 0 is, plug in 0, and this means that we can approximate the sine of x with simply x itself. So, by plugging in 2 degrees, we have to make sure that we return this to radian form. And so 2 times pi over 180, which is pi over 90 radians. And it follows from 8 with x equals pi over 90 radians that the sine of 2 degrees is the same as the sine of pi over 90, which is approximately pi over 90 using this formula here. And that is approximately 0.0349066. Well, if you take your calculator, make sure it's in degree mode, and calculate the sine of 2 degrees, you get 0.0348995, which is not that bad, actually. Off from this, it's actually a pretty good approximation. And again, that's the whole point. The point is that relatively or significantly small intervals, the sine curve, will look linear, and we can use the tangent line to approximate it. Let's just keep zooming in on that. And look what's happening. As we zoom in relatively close, it now looks like a line. And so the tangent line here would be a good approximation. Now it's going to be a different tangent line, okay? So if you change where you want to approximate, that means you're changing your x naught, then that means your tangent line is also going to change respectively to that, okay? Okay, example 4, find the local linear approximation of f of x equals the square root of x at x naught equals 1. Well, okay, I'm going to go back to my curve here, and I'm going to pop in a new equation here. We're going to pop in the square root of x. Let's see. Equation. View examples. So, okay, here's the square root of x. And according to this, we want to find a local linear approximation of this function when x naught is 1. So what we do is we zoom in on the region where x is 1. Zoom in. Already it's starting to look like a line. And here we go. So that's actually a pretty good region right there. So the tangent line would be a good approximation within this window of x values down here, which shouldn't be too bad. And then part B, use the local linear approximation obtained in that first part to approximate the square root of 1.1 and compare your approximation to the result produced directly by your calculating device. So first thing we do is we calculate the derivative, which is 1 over 2 square roots of x. And so it follows, looking all the way back to equation 6, that the square root of x can be approximated as the square root of x naught plus 1 over 2 square roots of x naught times x minus x naught. Now, if you leave the variable x naught there, then this just becomes the tangent line approximation to the square root of x anywhere you want. It's not until you actually plug a value in that it becomes the local linear approximation. And so once we plug in x naught equals 1, we get the following equation. And so now that we have the tangent line equation, we are going to apply the formula. So the square root of 1.1 can be approximated as 1 plus half of 0.1. Remember, we plugged 1.1 into here, and that gave us 0.1, which is 1.05. But if we actually calculate this in our calculator, the square root of 1.1, we get 1.04881. It's not bad. That's really not that far off. So the linear equation, the tangent line equation, is doing a pretty good job of approximating the function locally. Okay? In the last two examples, we used formula 6 for the local linear approximation. We could just as well have used formula 7. For example, with this formula, the local linear approximation of f at the square root of x at x naught is the square root of x naught plus delta x is approximately the square root of x naught plus 1 over 2 square roots of x naught delta x. Thus, to approximate 1.1 with this formula, we take x naught to be 1 and delta x to be 0.1. Plug everything back in, you get the same results. And so that's the essence of local linear approximations. Finally, let's go ahead and talk about error in local linear approximations and error propagation. As a general rule, the accuracy of the local linear approximation to f at a point x naught will deteriorate as x gets progressively further away from x naught. So in other words, the tangent line that we find becomes less and less like the function the further away you get from the point of tangency. To illustrate this point in example 8, or to illustrate this for approximation of formula 8 in example 3, let's graph the function e of x, where e is error, is the absolute value of sine of x minus x. Remember, equation 8 was this right here when we approximated the sine, where x naught was 0. And so we graph this, and we see the graph of the error, which means the further we get away, let's zoom in here. So everywhere this curve is close to the x-axis is actually a place where the tangent line is a good approximation. And as the curve goes up, the tangent line is getting worse and worse and worse in calculating the sine function. And so right about here is where it gets pretty 0.01 error away from the actual values. So this line right here is a threshold line, meaning we want our error to be less than 0.01 away from the actual value. And so we can see that the curve right about here, which is just a little bit less than 0.4. So if we get to about 0.4, then our errors are going to start being more than 0.01 away from the actual value. That's how you interpret the graph. In applications, small errors invariably occur in measured quantities. When these quantities are used in computations, those errors are propagated in turn to the computed quantities. And this is called error propagation. So make sure to get the vocabulary terms here in your journal as well. We will now show how to use a local linear approximation to estimate the error in a computed quantity from estimates of the error in the measured quantity. For this purpose, let's suppose that x is the quantity being measured, y equals f of x is the quantity being computed, x naught is the true value of x, y naught is the true value of y, delta x is the measurement error in x, and delta y is the propagated error in y. So the measured value of x is x naught plus delta x, and the computed value of y is y naught plus delta y. And we're interested in using an estimate of delta x to find an estimate of delta y. To do this, we'll start with our local linear formula. F of x naught plus delta x is approximated by f of x naught plus f prime of x naught times delta x. So in this formula, f of x naught is the same as y naught. So we can replace the following here in equation 10 with y naught plus delta y. Or we can simply say delta y, subtracting y naught from both sides, delta y is approximately f prime of x naught times delta x. Moreover, if we agree to let delta x and dx become the same thing, then delta y will become approximated by f prime of x naught dx, but f prime of x naught dx is the definition of differential y. So we can approximate delta y with dy, which tells us that the propagated error in y can be estimated by the differential of y at x naught, with dx interpreted as the measurement error in x. Okay, so although formula 11 looks nice on the surface, it's useless in applied problems because the true value of x naught is unknown. Keep in mind that the only value of x that is available to the researcher is the measured value of x naught plus dx, which is x naught plus delta x. To get around this roadblock, researchers use the observed value, x naught plus dx, rather than the true value, x naught, in computing the differential. This is usually satisfactory if dx is small, since x naught and x naught plus dx are close in value. We will illustrate how this works in the next example, but it will simplify our computations if we drop the subscripts. So in other words, we're going to approximate delta y with differential y, which by definition is f prime of x dx. Okay, let's go ahead and see if we can nail this concept down by an example. The radius of a sphere is measured to be 50 centimeters with a measurement error of plus or minus 0.02 centimeters. Estimate the error in the computed volume of the sphere. So what do we know? We know the radius of the sphere is to be measured 50 centimeters, but it has a measurement error of plus or minus 0.02 centimeters. Our goal is to estimate the error in a volume computation. That's our goal. We know that the volume of a sphere is v equals 4/3 pi r cubed. We're given that the error in the radius is about this much, okay? And we want to find the error delta v in the volume. If we consider delta r to be small, and if we let dr equal delta r, then delta v can be approximated like so. Delta v is approximately differential v, which is equal to 4 pi r squared dr. Now we substitute. R is 50. dr is plus or minus 0.02. We obtain the following. Change in volume, is approximately 4 pi 2500 plus or minus 0.02, which is approximately plus or minus 628.32. Therefore, the error in the calculated volume is approximately plus or minus 628.32 cubic centimeters. That's why this error analysis is important. It would seem that being off in the radius by a small amount really wouldn't produce being off in the volume by a very considerable amount. But we would be wrong. We could actually be off by a very large amount in calculating the volume. And that's the value of error analysis. If the true value of a quantity is q, and a measurement or calculation produces an error of delta q, then delta q divided by q is called the relative error in the measurement or calculation. When expressed as a percentage, delta q divided by q is called the percent error. As a practical matter, the true value q is usually unknown, so that the measured or calculated value of q is used instead, and the relative error is approximated by taking dq over q. Example 6. The side of a square is measured with a percent error of plus or minus 5%. Estimate the percentage error in the calculated area. So in other words, if I'm off by about 5% in either direction by calculating the side, how much am I going to be off in calculating the area? Well, the area of a square is x squared, where x is the side length. So differential area is 2x dx. I'm given that dx over x, which, how do I know that? This is a percent error. That dx over x is plus or minus 0.05. And I want to find differential a over a. But it follows from the two preceding formulas that dA over a is equal to 2x dx over a. This can be replaced with x squared, which gives me 2 dx over x. Now I can replace dx over x with the percentage error, and that gives me plus or minus 0.1. And so the percentage error calculated in the area of the square would be plus or minus 10%. So just as a review, by being off plus or minus 5% in the side length, I can be off plus or minus 10% in the area. In equation 14, we saw that dA over a is equal to 2 dx over x, which tells us that as a rule of thumb, the percent error in the calculated area of a square is twice the percentage area in the measured side. What rule of thumb relates the percentage error in the computed volume of a cube to the percentage error in the measured side, and why? That's left for you to think about. Now that we have defined differentials, every derivative formula has a corresponding differential formula. For example, if y is equal to the sine of x, then the derivative, dy dx, equals cosine x, can be written as a differential formula. dy equals cosine x dx. Moreover, all of the general rules of differentiation have corresponding differential versions. So d dx of constant equals 0 means that d of c equals 0. Here's the differential corresponding values. Differential constant times function is equal to differential constant function, which is equal to constant times differential function. Differential, or the derivative of f plus g, is differential f plus g plus df plus dg, and so on and so forth. And there it is. That's the homework. All right. God bless you, wherever you are today.